All right, so we don't know what a flywheel is, but we'll just draw a wheel, I guess. So we got a radius, and it doesn't tell us that, does it? It doesn't tell us anything.
No.
It's all symbolic.
It's all symbolic, yeah.
Okay, so we know that this flywheel has some sort of force acting on it, which is causing a torque. And so we can just go ahead and say we've got some sort of torque, and initially our flywheel is at rest. So let's say our torque is constant, our omega naught is 0, because it's not rotating at all. We have, so since we have constant torque, that means we have angular acceleration that's also constant. We want to get to omega sub 1. Which, yeah, so we're doing everything symbolically, so I can look at it again. So it wants us to express t sub 1 in terms of omega sub 1 and alpha sub 1, or alpha. Okay, so let's think about what alpha really is. So that might help to think about what acceleration is back in the days of linear kinematics. So we would often define acceleration as change in velocity over change in time. So now with angular acceleration, it's going to be very similar, but instead of using our linear type variables, we're going to use our rotational variables. So we're going to sub out the A for an alpha. We're going to sub out the V for an omega. Okay. So in this particular case, we know that, so change, or delta, always means final minus initial. So we want to take our final, which is omega sub 1, minus our initial, which is omega naught. And then our time, same idea, t sub 1 minus t naught. Now since we know that omega naught and t naught were both 0, whatever this number ends up being minus 0 is just going to be this number, same thing down here. So we can say that alpha equals omega 1 over t1. But we don't want to know what alpha equals. We want to express t sub 1 in terms of these two variables. So we can multiply the t sub 1 over and then divide the alpha to the other side. And we'd end up with t sub 1 equals omega sub 1 over whatever our constant angular acceleration is.